Thank you so much, everyone, for joining this session. I'm going to talk a bit about Apache Iceberg today and introduce a lakehouse architecture. We are not going with the jargon too much, but I'm going to try to break it down technically. And then we'll also talk a bit about interoperability. That's a huge aspect in today's table formats world. So I'm Dipankar. I'm currently a staff data advocate here at OneHouse. Before that, I was at Dremio. I was involved with Apache projects like Iceberg, Apache Arrow as well, mostly on the advocacy side and making sure like developer experience is good and like people get easier for people to get started with those ecosystems. More recently, I'm involved with Apache Hoodie as well, and one table. That's something new that we just launched today. And my previous roles has been in different roles, different segments like software engineering, data visualization, machine learning as well. So in terms of the key takeaways, we'll focus on, we'll start with the evolution of kind of data architectures, and we'll then go through how it has evolved over the years. Then we'll come to our prime topic, which is like Iceberg and table formats. And then we'll come to do a kind of a deep dive of the architecture of Iceberg and try to understand how various SQL queries work under the hood and how they leverage the kind of architecture. Finally, we'll end up with some design benefits and talk about one of the important aspects, that is interoperability. So over the years, organization has been kind of heavily investing in building like centralized, reliable, and scalable data platform. The whole idea was that if they could basically democratize data, they could have more data consumers like data analysts or data scientists to leverage it and further kind of enable analytical workloads such as BI, machine learning, streaming, those kind of workload. So data warehouse were kind of the first one. Data warehouse or OLAP databases are same to me. They were enabled to deal with that kind of like workload, more structured and relational workloads. But then it also lacked ability to deal with unstructured data for more advanced use cases such as AML and stuff. And I know today we are able to probably deal solve a couple of things around that with new cloud data warehouses. So then came the era of data lakes with the Hadoop ecosystem, which is on-premise. So data lakes were kind of great, right? Organizations could basically store all of the data, whether it's structured, unstructured, didn't really matter. And you could dump it in a file system like a Hadoop file system, and then with the rise of cloud and its kind of cheap storage, we have ended up with kind of object stores like S3, all three major kind of cloud providers like Google Storage, Azure Blob as well. So, the main benefit with this kind of system today is that we can basically scale out the story as we would like, right? And the other benefit is that we also have the cost factor associated towards that. So the cost in general is kind of less, and obviously there are other cost factors involved in that. But in general, the idea is that you could basically scale out the storage as you would like to. But there were a couple of problems, and of course that's why we're here today. So one is that you just can't dump all of your data, whether it's structured, unstructured, and you can just can't have your analyst or scientist to deal with that kind of data, physically stored data, right? So if you wanted to do something like BI, you still needed to organize the data and get it out in a form that is basically understandable by these different various sort of analytical tools, and then you can do your reporting analytical use cases around that. And the most the most important pinpoint thing that led to the evolution of the architecture that we are going to talk about today is that data lake, that they lack those kind of atomicity and consistency guarantees with transaction. So anything that you want to do, whether it's updates, deletes, even reads, you cannot do ACID-based transactions on the data lake. For example, like two concurrent writers are trying to write on the same table at the same time. That's kind of like tricky. You have those you miss out those guarantees. You don't know sometimes partial updates and those kind of things. Also, it was getting really hard. I have worked in various roles around this with data lakes. It was getting really hard to make sense of all of the data, right? Because, there is no real governance. There is no data quality checks. Usually, that kind of a data lake environment is like, a swamp environment. So really, how can we build a prediction model to solve something if we do not have that trust in the data, or how can we rely on some kind of analytical reports if we do not have that kind of quality or governance around the data? So this gave rise to a kind of a new architectural platform called Lakehouse, and you might have guessed it right. It's kind of like the best of the both worlds. So you take a data lake, take the best part of it, and then have a data warehouse. Data warehouses have great data management capabilities. So it allows you to take those kind of best abilities and from a new form of architecture that provides, most importantly, flexibility for different customers, different use cases. So this is more of a visual picture. I like to see things visually. Here are a couple of technical components involved and that we're going to discuss today. So I'll start from the bottom up, and then we also do kind of a comparison to like existing data architectures like data warehouses, and going beyond that kind of marketing jargon, lakehouse, and like how do we relate to a more technical component like a OLAP database. So obviously on the bottom, we have the data lake storage. This is where the data lands after ingestion from operational system, transactional systems, Azure Blob or S3 bucket, whatever it is, or it can be something like a Hadoop file system as well. So basically, it supports storing any kind of data and facilitates with like performance and security and those kind of aspects. So that's kind of the bottom layer where we have the storage. And then we have the file formats on top of it, and this is where the actual data is going to be stored, right? So, mostly, in the recent world, we have been using columnar formats like Parquet, Versi, which basically provides advantages with like, for example, the metrics, right? You could basically use those metrics to prune your, use the metrics for pruning your queries, and you can basically take advantage of that kind of thing. Now, the most important thing that lies on top of that is basically that table format, the lakehouse table format. And we will learn a bit more about table formats in the next slides, but in general, what a table format does is that it provides an abstraction. It provides that kind of abstracts that physical data structure's complexity and allows different engine to basically work on the same data, on the same table. So Apache Iceberg, Apache Hoodie, Delta Lake are kind of the three most popular table formats today, and are kind of gaining the widely, enterprise adoption. But obviously, this is not new at all. Like, in the past, we have had the Hive table format. Hive came out of like Facebook at that point of time, and basically led us to, Iceberg. And today, actually, one of the main motivations towards building something like Iceberg was the Hive table format and the problem Netflix were dealing at that point of time with Hive table format. And on top of that, obviously, we have the compute engine. We need an engine to basically crunch the data, so they're responsible for processing it, and depending on the task, depending on the use cases, you can use something like Spark, Trino, or Flink, or even, most recently, some of the popular compute engines like DuckDB, you can basically plug in there. Recently had a support for Iceberg as well to read the table at least. And, so really, like depending on the use cases, the idea is to bring your own compute engine and connect to the table format versus the other way. And finally, the final component of the lakehouse is basically, obviously, the analytical tools, that are responsible for like, downstream, analytical applications like BI, reporting, ML-based tools as well. And these tools are, the idea is that you can connect to these tools where certain systems like, in the past we have used ODBC and JDBC, but more recently we have seen use with like something like Apache Aeroflight, Flight SQL that gives you the semantics to query those data and be able to deal with it in a more efficient way. So one question that always came to my mind when I was kind of getting into this kind of lakehouse architecture, understanding a bit more technically, was that how does it compare to an existing data architecture like a data warehouse, right? So the main distinction between data warehouse architecture and something like this is that each of these components that you see here, they're no different. They're no different in a OLAP database or a data warehouse. Basically, the storage that you have, the table format, the file format, the compute engine, they are all the same in a data warehouse environment as well. The only difference here is that here you do not have each of these components bundled into one single system. Whereas in a data warehouse, these components are bundled into one unified system. So that brings us to like the question, okay, what is the difference in that? So the difference in that is that these data warehouses have been like using table formats and file formats. They have been building their own table and file formats, and they are optimized really for their own compute engine. So that means once you load the data into their own table and file format, it's really hard to get, like, bring a different engine to that same kind of data and table format and, plug into that. So that means, in a way, you are locking the data to your own environment. However, in the recent days, we have also seen a very good move around that. Like, cloud data warehouses vendor like Snowflake and BigQuery, they have started, supporting external table formats like Iceberg. You can basically, manage them as their own way. And that allows you to, that allows customers, like, to deal with various kind of use cases that they were kind of, restricted to in the beginning. So we recently also published a paper about it, and in general, that's the idea, like just to establish like how it compares to like data warehouse technically and how this relates to a data warehouse. And obviously, like there are on top of that, the benefits out of it, like we talked about, like the scalability, the data management capabilities that we kind of see now. So what is a table format? So usually with databases, we have obviously seen the concept of tables. It's not a new concept at all. Like vendors like Oracle, have been doing it, or Microsoft have been doing it with relational databases. basically it's a way to organize data sets file to present them as a single table. So users don't really have to know the kind of the physical bytes and the files, and they can just have that abstraction, right, on top of that. And in the past, like I said, vendors had their own kind of storage engine that kind of handles the data on the files on their disk, and the execution engine interacted with their own files, right? Now in the big data world, with Hadoop and HDFS, we ended up ultimately with the Hive table format. Now Hive, like I said, it allowed more users to be able to get hold of the data that was stored in a file system like Hadoop file system. So in a way, it allowed the democratization of data using something like Hive query language, which is pretty similar to SQL. So with Hive, the way it was designed is that with a Hive, a table is basically a set of directories. And each of these directories will have the files, which are basically the file that the engine has to deal with, right? And so, like you see here, it's a table with a couple of like folders here, and the folders have their own files. And the tracking is kind of done at the folder level with the Hive table format. So let's talk about it in some more details. In the Hive table format, like I said, the tables have one or more directories. Obviously we see here one of them or a couple of them, but at scale this would be like a lot of directories, right? So this has been kind of the de facto standard since like the mass adoption of Hadoop, and so definitely it being the kind of the de facto standard until now, at least I know a couple of organizations still leveraging on Hive. That has some advantages towards it, and of course we are going to talk about advantages and then slightly move on to the problems that kind of Netflix face around them. So one of the advantages was that it basically works with every engine, right? Until like recently there was no other table format that allowed you to do that. So that was great. Secondly, it had more efficient access patterns. So for example, things like partitioning schemes, and mapping to that column, bucketing, and so you don't really have to do full table scans for every query that you run, right? So that was great. It was also file format agnostic, so that means you can use any kind of file format, whether it's Parquet, CSV, doesn't really matter. It's agnostic towards that. And the most important thing is that you could atomically update a whole partition. So for example, you can basically take a partition, change the data, whether you want to do some, insert some records or delete or upserts, and write data into a new partition. And when you're writing it, there is no one sees the changes, right? No one sees the changes, and then you atomically swap that reference of the, the pointer in the Hive metastore. And this kind of gave us the Hive metastore, right, and allowed us to deal with things like atomicity, consistency guarantees, etc. So the Hive metastore provided kind of a single centralized answer to what's in the table. Like if I as a user or any kind of query engine comes to the table, the Hive metastore basically allows you to basically have a single centralized answer, and kind of every user, every query tool got the same kind of answer. But obviously, like, this kind of advantages also brought us to certain caveats, and this is not me throwing shades on the Hive table format at all. Obviously, like, this is a great inspiration to what we have today. But some of the problem that I also personally saw during my work life was that the smaller updates were kind of very inefficient because you can only atomically update whole partition. If you only wanted to change a few records and a more number of time, that's very inefficient with the Hive table format. Then you had no way to change data in multiple partitions safely. So because if you want to insert, let's say, a row in two different partitions, you cannot possibly do that with atomicity guarantees in Hive. Same things with multiple jobs doing the same data set. If there are multiple jobs trying to access the same data set and do things like concurrent writes, it's really hard to do that. Most importantly, in the Hive table format, the files are under the folder. We kind of like established that, right? So engines basically are not going to read the folder. They're going to have to open up each and every folder and then open up each and every file and read the file, close it, and imagine this doing at scale. Like, this could be like a lot of time-taking task. Another important aspect of like where Hive kind of lagged was that user kind of had to know the physical layout of the table, and that's kind of a really like a cumbersome thing to deal with. Like, for example, if you have a table partitioned by day, and if your query has something like a timestamp, Hive really will not know that kind of mapping. Hive didn't have that mapping. So unless and until you specify that partition column that you have explicitly defined for your Hive table format, your users will basically, if they run a query, pass a query, they will basically be doing full table scan of the query of the table. So ultimately, it's also a matter of educating people. Like, that's what I also realized, that, let's say if a table is like I said, if a partition by day, why do users really need to know about that kind of like, okay, 2022/08/01? Why do they even need to have that kind of like knowledge around that? And most importantly, the table statistics in Hive are kind of often stale. Like, we have realized that, at scale, the Hive allows you to basically gather this kind of, statistic in a kind of asynchronously. And these kind of read jobs are very expensive at scale. And to collect these stats, we have to run this job, most importantly, and you have to schedule and do some maintenance around it. So they are hardly run, in practice. But these table statistics are really efficient, in able to like, query planning for query planning and pruning the data and accessing the data in general. So these problems are pretty much common, like, at every organization at scale, these are not new at all. And Netflix were kind of the main one to look at it, and they went to the drawing board and, they thought about it, and they decided that instead of putting a Band-Aid to kind of each and every problem of this, can they really take a step back and understand the actual issue? Because in the long term, it was going to be really hard to, manage it. So they had these goals they wanted to achieve, and, these goals are, again, very similar to every organization that, we want to achieve it. So one of the first goals was around table correctness and consistency. I talked about it. You need to have the trust in data. Otherwise it's really it becomes difficult to make that decision. And irrespective of the query engine that you use, all the queries should return the same result. Next is around faster query planning and execution. So one of the queries that took them basically 10 minutes to plan a week of data for just one metric. It's just one metric of data for a week of for a week's filter, and it took 10 minutes to basically query that data. And users are not really going to have to wait for that. Performance is really a key around that. Next, we talk about the physical layer of the data, and we understand that it's super important to have that, like with partitions. Even if I have to query using a date, users should not be having to worry about that. So we can just have the software take care of that. There were also a lot of problems with table evolution, and this is something we usually see, right? Tables grow over time. We should be able to, like, business requirement change. We should be able to adapt to new requirements that comes in the table and be able to evolve the schema without doing things like, for example, rewriting the entire table. That's a very expensive thing to do. So, this kind of it was an important aspect towards them as well. And to accomplish all of these at scale, if we can take care of this probably for a smaller data set, but imagine dealing with like a huge petabyte table data and it only grows, so it's really hard to deal with this at scale. So when looking at this kind of the Band-Aid problems and intermediate solutions, all these cons they went through, they realized that they could solve this using a pretty simple solution. So the solution was that instead of tracking the the files at a folder level, they just get rid of the directory structure and track at the file level. So that is the only difference that kind of exists between like table formats today, like Iceberg versus Hive. And that's really the core, like that basically set the precedence for that. So this is where Iceberg comes and kind of addresses this problem. I'm going to talk about what Iceberg is and isn't, because it's better to have that context, because we have seen that with Hive, it can be quite nebulous and mean different thing to different people. So what Iceberg is, it's obviously a table format specification. It's a way to lay out those bytes and in the form of table, giving that abstraction on top of the file formats, like Parquet. So it's a set of libraries and APIs, and basically if you're an execution engine like Spark, you will basically have to leverage those APIs in a more technical sense and be able to interact with those libraries. It's not a storage engine, it's not an execution engine or any kind of like a service of any form. So I'm going to do a kind of architectural deep dive and go through like how Iceberg is like developed and how it's set up architecturally. So as you can see in the image here, there are basically 3 layers of at a high level for Iceberg. So we'll go from like the top to bottom and to understand the various components. The first is the kind of catalog layer, which is basically a super important component, and Iceberg needs this component if you're trying to deal with things like atomicity and consistency guarantees. The second is the metadata layer, and the metadata layer has things like the metadata file, the manifest list, the manifest file. I'm going to talk a bit about what they are as well. And finally, the data layer. This is where the actual data is going to be stored. These are our Parquet files, our org files, and this is how the overall architecture looks like. So the first thing here is the Iceberg catalog, and so if a user is trying to basically read or write data for a table, they first need to know where to go, and catalog is that place. So in a more technical sense, this can be anything like a data store, a database. The only requirement for something to be a catalog in Iceberg is that it should have it must be able to support that kind of atomic operations, right? Basically what we want to achieve through that is that once a query engine writes something to Iceberg table, it swaps the reference of the version of the metadata file with the latest one. So for example, if version 1 is the current metadata file, and if I do some upsert, I'm going to, as an engine, I'm going to change the metadata file in the catalog to version 2. So now that allows me to get basically all the latest stats. So for example, now if I bring any other query engine like Trino to read that data, I will still see the fresh set of records because my version is now the version 3, which Spark has already basically reiterated and changed it. So that's the overall concept with, catalog, that you can basically store as much of data as you want in a data lake storage like S3, but you need some kind of a locking mechanism for those atomicity and consistency guarantees. So most data lakes, they don't provide that, and Iceberg catalog, they serve this purpose. So the catalog can be a lot of things, like I said, it can be technically any data store, Hadoop file system as well. Of course, we don't recommend using the Hadoop file system as a catalog in production because we have seen losing those kind of guarantees when we're doing concurrent writes and stuff. But their Hive meta store is one of the commonly used. If you're in the AWS ecosystem, maybe AWS Glue is a very common like catalog as well. Or there is something called Project Nessie, which is open source as well, that allows you to get, deal with things like, a Git-like code. So for example, you have a production table, you can create a branch of it just like a GitHub branch. And you can basically create that branch in isolation, like a local development environment. And you can write your ETL job or whatever it is in that particular environment. And no one sees that when you're doing that. And then once you're done with that, you can basically say, hey, merge this particular branch into the main branch. And then you make the data available in production. So that's where things like, write, audit, publish, and, those kind of guarantees come into the picture where you can do more, detailed data quality checks, if I may. And like I said, in a more technical sense, what the catalog is storing is the version of the location of the current metadata file. Like, okay, this is my version 1, and this is where that location exists. So let's say if you're running a select query, like a select star from something with some limit, you basically go to the catalog and say, hey, give me the current metadata file for this particular, at this particular state of the time, and it gives you that particular location. So once you get that particular location, I have numbered it with 1, you go and find that particular, like the snapshot, and you get the current metadata file from that. So the metadata file, as the name suggests, it's a metadata about all the tables, certain properties like schema, like partitioning specs, and those kind of things. So you see, obviously, a couple of the contents here. I don't know if it might be not visible as well totally, but in general, what we are trying to have here is things like snapshot is a very important concept here. Obviously, snapshot means the state of a table at a given point of time. So basically, whatever operations you do, like creating a table, writing it, any kind of insert, upsert, everything is captured as a snapshot in Iceberg. And finally, from that particular current snapshot ID, so basically in the catalog, you got the location of the metadata file. Let's say this is the version 1. And from that metadata file, you got the current snapshot. Okay, this is my current snapshot. And using that current snapshot ID, you can also see the manifest list location. So that has a lineage towards the manifest list. So it points you to that manifest list and brings us to the manifest list point. So what is manifest list? Basically, manifest list contains information around things like partition, most importantly. So you can do like, at a high level, you can do things like partition pruning here. So you don't really have to, go and read data from each and every partition. You can basically, read, the query engine can read the manifest list, and it can get information around that. And from that, you can basically find the manifest file, which is what we are looking for the next step of our, journey. So the manifest file, it's at a lower level, it's tracking those data files, like those Parquet or the org or whatever file is that, they're tracking it at that particular level. And obviously, we have information such as the data file path, and most importantly, the statistical information that I mentioned about. Like, for example, Parquet gathers those, Parquet has that information in the footer, right? The lower and upper value bounds, and the null value counts and stuff. But instead of like going and opening each and every Parquet file, what Iceberg does, it does a second level of aggregation. So it basically aggregates those statistics into a manifest file so that you just can come to the manifest file and basically prune your data files based on the manifest file. So you don't really have to open and take the overhead and the cost of opening each and every Parquet file, even though you know that you can do that and take advantage of things like pruning. So this may seem like a lot, but at the runtime, this is way faster, of course, and we can see more about it as well. So I wanted to run through a couple of the queries that are very basic ones, just some couple of writes, couple of reads, and then we are going to see how the Iceberg architecture look like, how the system look like in the data lake as well. So let's say first we create a table. It's a simple create statement, and we have a couple of fields here. We are partitioned by order of by hour of order timestamp. As you notice here, we haven't introduced any new partition column here. The order timestamp is part of that particular table, right? The only thing that changes here is the hour transformation. So Iceberg, it allows you to do kind of transformation and keeps a track of this transformation from here. So on the right-hand side, you have the architecture of Iceberg. On the left-hand side, you have the catalog and the file system, whatever it is, S3 or whatever file system it is. So as you can see here, because I don't have any data inserted at this point of time, you just have one metadata file. That's why you don't have the manifest list, the manifest file, and the data file, because obviously we haven't written anything towards it. And that gives us the ability to, see that, and basically now we have one version of the snapshot that is the current snapshot. So now let's go ahead and create our, insert some record into that. So if we insert some records here, now we'll see the tree of the iceberg that we see, because now we have inserted some new records. So now we have a version 2 of the metadata file. As you can see, there's a different metadata file, and you also see that it has 2 snapshots in that metadata file, right? There's a snapshot 0 that was from our previous create table, and there is a snapshot 1 that is based on an insert statement. So Iceberg keeps a track of all the older snapshot. That brings us to the question, okay, what does it mean for storage? At a point of time, it might be a lot of storage, like a snapshot. So obviously, there are maintenance procedures to do that. If you're using something like Spark, you can call a procedure, and you can schedule your maintenance to get rid of all the older snapshots. So this is basically used for things like time travel, right? Because you want to time travel to a particular point of time, and you want to leverage those use cases. And finally, if you see here, the catalog, if you see, now the catalog is updated with the version 2 of it, not the version 1. So because whatever engine used it to write the file, basically changed that reference to version 2 from version 1 now. For the lack of time, I'm going to skip the upsert, but it's kind of the same thing. You do upsert, there's a different metadata file now, we have a different snapshot now, and you have a different kind of tree, but ultimately the thing remains the same. One thing that is important to understand here is that with upsert, on the left-hand side, if you see the files here, we have some grayed out files, and we have some newly written files in a new partition. The reason being that is because you are trying to basically use a strategy called copy on write, and you can also leverage something called merge on read, which is also very efficient for streaming-based workload. So here, basically, all the new updates are basically written to a new file instead of the older file. So the read statement follows a similar way. You go to the catalog, get the current metadata file. We talked about it. We get the current metadata file. From that, we go to the manifest list and find the exact data file that is required for a query to serve the purpose. Time travel works in a similar way. The only difference is that, let's say, for our timestamp, we have specified a particular time travel, field, and in that now, because in the metadata file, Iceberg keeps a track of all the snapshot. In the snapshot in the metadata file, it will have the timestamp that we specified in a query, and based on the timestamp, it basically go through the same route and find out. So the difference that you see here is now that we are not fetching the latest set of record, it went to the snapshot 1 and pulled out the other set of record that was from our insert statement before the upsert that we did. So again, I'm going to skip this. This was basically, linked, Netflix, basically, they had this time that was taking 10 minutes to just, plan the query, and with Iceberg, it took them basically 42-second wall time just to execute the query overall. So that brings us to the main question: how do we choose one? We have discussions today with different table formats, we have Iceberg, Hoodie, Delta Lake as well, that are really gaining adoption. So the decision to choose a specific table format is very challenging and can be involved in a lot of cost. I was personally involved in a lot of this discussion in the past year. One of the main things that we have come to realize is that obviously it comes to feature level comparisons, complexity of implementation, how easy it is easier to get started and scale it, right? And of course, the main thing is the support by the query engines and the ecosystem overall. So if you're in a, in a Google environment, you might have a different set of compute engine. So you want to be able to get support from these different environments. And with newer workloads, we are also realizing now that these table format needs to be interoperable. One of the customers that I was talking recently is that they have these 2 different table formats that they're using, and it's kind of has also led to kind of a siloed environment, and they want to be able to leverage them. So that brings us to the focus on interoperability. Can we make these table formats interoperable? So the question is really, do we have to choose, or there is another way? And there is another way, because at a very fundamental level, if you see this metadata structure, they're basically a metadata layer on top of the file formats, right? And all these different table formats, like Hoodie has this Hoodie metadata folder on the Parquet file. Delta has the same log file and the Parquet file. Iceberg has the same kind of thing. So ultimately, it's an abstraction on top of that. So basically, it's easier to be able to take those metadata file and translate them into another format, and that's another project that I have been working on, and with a set of committers from my organizations and Google and Microsoft. That's called One Table. That basically we released today, and it has focus on interoperability. So you can basically, the idea is that you can take a particular source table format, like you can write in your particular choice of table format, like Iceberg, and depending on your use cases or your choice of compute engine, you can translate them into one or more formats. That's the idea behind One Table. So one table, it's omnidirectional. The reason I specify on the term omnidirectional is that Databricks also released something called uniformat. That basically works in one single way, whereas one table will focus on, like, you can take, go from any direction to the other direction. So it really isn't dependent on one way of doing things. So the idea is that you can take any table format of your source, and you can see the Spark, you can read it in different table formats. So if you're interested in this particular open source project, it's very new. If you're interested in contributing or applying it for your use case as well, this might be something interesting. So, give us a look on that. And, we are also planning to incubate it as an Apache project, because we have been involved with various contributions from Google and Microsoft today, and we are seeing more active contributions from Apple, Adobe, and other companies today as well. So that is pretty much it that I had today, and thank you so much for having me, and I might take any questions that you guys have.
Thank you.
I know I exhausted that. I'm sorry about that. Yeah.
No worries. You're still on time. So we can take a couple questions before, kind of going for lunch.
Thank you for this talk. My question is, does any of the table formats that you described support the multi-query transactions, like where you begin the transaction, then make a couple of updates, then commit or roll back it all together?
Yeah, so quite recently, the Iceberg with the REST catalog specification, it's a specification that allows you to do, use something like a REST API. That is something that is being worked on that I know of, that allows you to do kind of like, if I'm not wrong, you're talking about multi-table transactions, right? Where you have, a couple of transaction tables that are dependent on, like, for example, fact and dimensions, and you make changes at the same time and you're exposed to the new production environment, right? So that is something that is being worked on. Project Nessie is something super interesting as well. Like, it's open source project that allows you to do that. But by default, Hoodie or Delta Lake doesn't allow that if I know it. But I know Hoodie, something is being worked on the Hoodie side as well.
That's a great update. Thank you.
Of course.
Thank you. Yeah. Anyone? Yeah, right there.
Can you say a little bit about all the different indexes we have from Hoodie to Delta Lake, data skipping, global index, and so on?
Yeah.
And Iceberg specifically, where it's lacking.
Right. So Iceberg doesn't have any concept of indexing at a high level. So Hoodie is one of the table format that really brings out those kind of rich indexing, experience. But Iceberg basically, tries to deal with the manifest files. So that's the way they took it. And so basically, you do not leverage an index to do that. Whereas Hoodie is more dependent on different kind of index, like Bloom filter, simple index, or those kind of things. Whereas that's something that is kind of like, as far as I've realized, that that's something that is not present in the Iceberg environment. And I'm not sure about the Delta space as well.
Yeah, they have data skipping as well. And
right. It's the same kind of thing.
Not all of it's open source, unfortunately.
Right. Yeah. Yeah. But yeah, Hoodie, of course, has a more diverse way.
At the beginning, you talked about small updates issue, right? Of course, I'm not seeing small update issues as a data lake issue in general, okay? But I'm not clear how you are solving that based on the presentation so far.
Yeah, I think the whole idea behind this is that, for example, like upserts, right, and those kind of thing, right? Now you don't have to be able to for example, like I talk about how you have to basically atomically swap the reference every time you do those kind of updates. Now you can do that without doing that, right, with Iceberg or any kind of table format. So basically you can write the data and this copy on write or the merge on read update. So basically you can use this technique and balance this kind of write and read latency trade-off. So for example, if you have something like Flink, you're writing quite frequently, right? So you can basically use technique like merge on read, and you can, what Iceberg or Hoodie does in a different way as well. But what Iceberg does, it basically merges these things on the read side versus the write side. So that kind of trade-off is being involved in this kind of new techniques.
I see. Thank you.